So this is just a quick little video to help you in case you get confused working your gas law problems today during class. So we're going to do one example problem from each section just to help guide you along. So pressure is measured in several different units. The most common in chemistry are mmHg, which is millimeters of mercury, kPa, which stands for kilopascals, and atm, which is atmospheres. You can convert between these units using the conversion factors shown on the screen. So whenever you're doing gas law problems, you want to make sure that all of your units are consistent so that your math is going to work out properly. So for the first question, we have 52.5 kPa over 1. And we want to convert this into ATM. So this means that I need to put kPa on the bottom here, kilopascals, and I need to put my desired unit on top. So according to my conversion factors, 1 ATM is equivalent to 101.3 kPa. So if I do this math here, I'm going to need to do 52.5 divided by 101.3, and that's going to give me an answer of about 0.518 ATM. Now this answer makes a lot of sense because 52 is roughly half of 101, so we expect our answer to be something around half of an atmosphere. Now, volume for gases is typically measured in liters or in milliliters. Now, in most gas law problems, you want to actually solve using liters. So it's going to be useful to be able to convert between these different units. So if I have 4.293 liters and I want to convert that into milliliters, I'm going to put units of liters on bottom and milliliters on top. So 1 liter is equivalent to 1,000 milliliters. So to solve this problem, I pretty much just need to do 4.293 times 1,000, and I get this. Now, whenever you use temperature in gas laws, we're going to want to use the Kelvin scale. So the Kelvin scale is the absolute temperature scale that is used in gas law calculations because it starts at absolute zero, 0K. So this is called absolute zero, and it is the temperature at which all molecular motion theoretically stops. So this is a theoretical value. But we know that when you heat a gas, that it increases its kinetic energy. So there must be some point at which there is no kinetic energy, and that would correspond to a temperature of 0 degrees Kelvin. So unlike Celsius, this has kind of some arbitrary reference points like freezing and boiling of water. Kelvin uses a direct proportional relationship between temperature and kinetic energy. So this ensures that gas law equations work correctly without getting those negative temperature values. So you can imagine a question where maybe you're solving for volume and you have a negative temperature in Celsius. Well, your answer can't be a negative volume. So we need to use a temperature scale that doesn't have negative numbers. So if you want to convert from Celsius into Kelvin, you just got to add 273.15. So if you want to go from Kelvin to Celsius, you would need to subtract 273.15. So if I have 300 Kelvin, that's going to be equal to degrees Celsius plus 273.15. which basically means I'm going to subtract 273.15 from both sides. So when I do that, this part cancels, and I'm going to be left with a temperature of 26.85 degrees Celsius. This next question is a combined gas law problem. So the combined gas law is this: P1 V1 over T1 equals P2 V2 over T2. So the ones, P1, V1, T1, that all refers to the initial pressure, temperature, and volume. The twos refer to the final temperature and volume. Now, when you have a problem that says one of these variables is constant or it just doesn't mention the variable at all, that pretty much means that you can just cancel it out. So if we look at this question, it says a sample of nitrogen gas has a pressure of 6.58 kPa. So that's pressure 1 at a temperature of 539 Kelvin. So that's temperature 1. If the volume does not change, so in other words, V is constant. Or you could also think of it as V1 and V2 are the same number. So because of that, because it is a constant, we can remove that from our math here. It says, what will the pressure be in ATM? So that's P2. What will it be at 211 Kelvin? So we need to solve for the final pressure of this system. So let's go ahead and start working on that. So P1 we said was 6.58 kPa. We said that T1 was 539 Kelvin. P2 is what we are solving for. So you can think of that as X or question mark. And T2 is 211 Kelvin. Now, since volume is constant, I can actually simplify this by removing volume. So I'm left with P1 over T1 equals P2 over T2. So I'm going to plug that into this equation. So P1 over T1 equals P2 over T2. So that's going to be 6.58 kPa is equal to, I'm just going to put P2, that's the variable that we're solving for. You could also put X if you prefer, but we're just solving for this variable. And T1 is 539 Kelvin, and T2 is 211 Kelvin. So there's a couple ways you can solve this. You can find the ratio first and then multiply by 211. You could cross multiply if you prefer. So I'm going to go ahead and cross multiply. So I end up with 6.58 kPa times 211 Kelvin is equal to P2 times 539 Kelvin. So to solve, I'm going to divide by 539 Kelvin on both sides. So Kelvin will cancel, and this math will give me P2. So I need to do 6.58 times 211, and I need to divide that by 539. So when I solve, this is the answer that I get. Now, notice that Kelvin and Kelvin will cancel, which means this answer is in kilopascals. Now, if you look at my answer, though, those numbers don't match, and that's because my units are wrong. So I want to convert 2.576 kilopascals. I need to convert from kPa into ATM. So from my conversion factors that we saw in the previous problems, I know that 1 ATM is equivalent to 101.3 kPa. So I'm going to go ahead and divide my 2.576 by 101.3 kPa, and then this is going to give me my correct answer, which is 0.0254 ATM.